one of the things we're going to talk about, and this is just a agenda, who is AECOM, our technology, how it's going to work to meet TMDLs, and what the next steps are. I'm going to just scroll down to the next slide. All right, so go ahead and go one more slide. So AECOM is a Fortune 500 company. We're in 40 countries, and we're, I believe, the only large company right now that has developed a research think tank to study harmful algal blooms. I started that 7 years ago, and we started looking at issues in Florida because Florida had, at that time, devastation. The governor went ahead and declared a state of emergency in 2 years, in 16 and in 18. We had 7 counties shut down. The state itself, over 1 month, lost over $385 million in tourism. So we took it as a serious issue. Then we worked with Congress, we worked with the universities, and we worked with the Army Corps of Engineers. And this became a federal issue. Next page, down. And because of that, we spent a lot of time in Florida, as you can see from the slides there. The focus was on what we can do nationally. When Congress authorized the WRDA bill in 2018 after the Florida disaster, the Army Corps of Engineers, AECOM, and a DOE lab known as Pacific Northwest Laboratory partnered on habitats. Habitat stands for Harmful Algal Bloom Interception, Treatment, and Transformation System. So this was essentially our federal government saying we have a national problem. We need to look at new and innovative ways at how we can treat harmful algal blooms. So the intent was, if we can take harmful algal blooms out of the water as an interception, we can then return back clean water, but then take the biomass, the algae that comes out of the water, and transform that into a fuel. That was called habitats. That won numerous awards. We've been working throughout the eastern part of the country at this point. But the real takeaway is when you look at algae and you look at the components of what's in algae, 70% of it's carbon. The rest is nitrogen and phosphorus. So if we can let algae do the work, essentially work with nature, algae's doing all the heavy lifting. They're taking the CO2 out of the atmosphere. They're taking the nitrogen and phosphorus out of the water. But if we can take that algae cell, that microscopic algae cell, out of the water rapidly without rupturing or lysing the cell, then if there's cyanotoxins present, we can take those out. So what we do, and you heard about the nanobubbles, we do that on a side stream process. So essentially we bring in the water and separate that. We're using dissolved air, very similar. We create the nanobubbles, and then we can filter out the algae. We can absolutely separate that, float it to the surface, and then we can skim off the algae and return back highly processed, clarified water, which is also oxygenated. So I'm going to walk through the technology now. If you go down one more slide. So what you can see here, if you can scroll up a little bit further, scroll down, perfect, stop right there. So the lake water, this is a standard lake water look. Essentially, you really don't have an Asuki disc look. You might have a few inches, a foot, a couple of feet. But when you go through the process that we go through, the hydronucleation system, it clarifies the water. So essentially, you get crystal clear water. That jar on the right is the algae. That's what comes out of the water. So essentially, we take that green water jar that you see up there, and we can process that rapidly to take, in this case, the microscopic algae cells out rapidly, return back clear water. And then we have that biomass. That was really our first phase. We said, we pretty much mission accomplished. We can take the nutrients out of the water. We can bring highly oxygenated water back, get all the benefits from doing that. And then we can just dump out the algae. But that didn't really solve the problem. We wanted to go a step further and come up with a sustainable solution, because this was not just a Florida issue, wasn't a U.S. issue. This is a worldwide issue. You don't have to look far. You can go to China to see how bad it is with 1.5 billion people there. We really started looking at that a decade ago on Lake Tai, which is the size of Okeechobee, solid green. They have huge harvesters out over there. So that kind of led us to this process. So when you look at this, especially for the wastewater folks here and the water treatment folks, it's a clarification process. But we do it in a way that allows us to keep that algae cell intact. And we do it rapidly. So by adding the nanobubbles to our system made all the difference. And you can see on the slide there, that's the algae that comes off the system. That's a 2% solid. It handles just like any other solid. And then we can go through a dewatering process and turn that into an algae paste, or in this case, a cake, which is about 15 to 20% solid. That essentially allows us to do a lot of different things with it. At the liquid phase, we can turn that into fertilizer. We just finished a project with the EPA and the University of Florida. We have been able to show that the algae was able to displace 50% of commercial fertilizers. So as we look around and say, well, where's all this nutrient sources coming from? Agriculture is number one. Septic tanks, number two. So if we can find a way to get a sustainable agricultural system in, that's a great thing. So that was what we can do with the slurry. We can get it to a paste. We can turn that into a pellet. We can dry it. There's a lot of uses for it. Next slide down. So that's what it looks like. And I think everybody here in this room knows the value of carbon, knows the value of algae. But that's the essentially the product that we can get out of a lake or out of a nutrient-rich water body. And for us, especially here in California where water is so valuable, having a sustainability element is needed. We have to find ways to do closed-loop systems. We just can't continue status quo. Just recently, for those of you who follow Florida water, a couple months ago, we had spinning fish. Fish that just now start to go in circles. We're having sawtooth fish that are beaching themselves. We're having problems with dolphin. You can Google them. It's horrific, right? We all know these issues. So we have to find a way to solve these problems on a sustainable level. So this is another tool. By physically taking out the algae, we're now coming up with something a little bit more on a permanent basis. And if we can add that element of sustainability, then we have another valuable asset. So, as I talked about, that's the fertilizer. That's just taking the slurry out. We were working with a nursery under an EPA grant, so we were taking excess algae out, but we did test trials and plots. That information is going to be published later this year, but we were able to show that the algae was able to get the same plant height growth, 100% algae versus 100% mineral fertilizer. But we looked at the seed crop on this particular crop that we were looking at. It was more of a 50-50 blend that got us to the actual seed yield. So on a conservative basis, we're able, on a first trial, to show that the algae fertilizer can displace 50% of commercial fertilizer. So that provides a huge value. The next one is the fuel. And I'm sorry, go back to that one slide over there. That middle one, this is when we were working with the Army Corps of Engineers, Department of Energy. This process is known as hydrothermal processing. The technical word is hydrothermal liquefaction. Essentially, we're taking the carbon that's in the algae, 70% of that algae cell is carbon. We can take that under heat and pressure, just like it does in geology. We can turn that into crude oil and renewable natural gas. So that was really what the federal government was looking for. How can we create sustainable fuel? And for us to do this at scale, since we don't have hundreds of harvesters or millions of harvesters out there, we looked at biosolids. And biosolids fits in perfectly. That's almost a drop-in-place feedstock. So in these kind of projects, we're looking at blending wastewater biosolids with algae and other wet waste to create a sustainable fuel. Now, the other unique thing about hydrothermal liquefaction, at the temperature and pressure, the temperature gets up to about 350 C, the pressure goes up to about 200 bar, or 3,000 PSI. At that level, we can break PFAS. So now we have a solution where we can not only create energy, but we can solve the forever chemical issue. We'll be conducting a detailed research project on that later this year, where we're going to be spiking the 9 elements of PFAS that are currently being regulated. So there's solutions that are out there. There's also one that's been out in the market for some time, and it's taking the algae and using it for commercial products. It's right now, I think, in about 150 shoes, using that as now a biofoam product. So there's a lot of good value that's coming out. So as we look to the future, we're starting to see that there are a lot more tools coming out as we start to address this issue of nutrients. Okay, so now let's go into the TMDL levels and what everybody cares about, Lake Elsinore. So when we looked at the phosphorus levels, and these are some of the numbers and projects that we've done around the country, Elsinore comes up pretty high on this phosphorus levels. But what our system does, as we talked about, we can get the phosphorus down to below detectable limits. And that's kind of a aha moment for physical separation. So really doesn't matter what the concentrations are in the intake water. The system itself was able to physically take that out because algae is doing most of the work for us. But these numbers are scary. These are high levels of phosphorus that are in the lake. Next one over. Nitrogen is a little bit much off the chart. That one is the highest one we've ever seen. But again, what this physical separation process does, it takes out nitrogen and phosphorus and carbon, and if there's cyanotoxins, they come out as well. So it's a physical process, but you can kind of just see what we're dealing with. So when we look at the TMDL levels here for Lake Elsinore and what would be done, how many harvesters would be needed, those kind of things, we kind of put together a schematic here so we can kind of look at that. And we look at one harvester and we go down to 10, we're talking about meeting 75% of the TMDLs. So there is potential here that this is another tool that should be looked at. We're going to be conducting our research project here that got funded through the SAPA project and the Prop 1, Round 2. So we were originally planning on putting it right there on the beach at Launch Point, which is now underwater. So we'll probably have to work with the city and find out exactly what would be the ideal space to put that. But we'll have a 1 MGD harvester here. We'll set it up, we'll run it, and again, it's very visible. You'll be able to see the water come in, the water come out. Usually there's a lot of media that follow that because it's just fascinating to kind of see the amount of algae biomass coming out. What we did for this project, for Lake Elsinore, we're going to take the biomass over to the CRR facility. They're going to use it in their digesters to essentially create now a RNG, a renewable natural gas. But as the systems get bigger, then these things could be scaled and clean energy plants could be put right next to them. Again, we're talking about moving water, so these could be piped anywhere. We've put them on barges, we've put them on land, we have these on wheels. So the idea is to be flexible and mobile. These things can plug and play, essentially. So as an example, go ahead to one more slide down. And picture. So this was our vision. This is kind of just a rendering of what it would look like. That's the clean water going in. So essentially, if we pump in 1 million gallons, we pump out 1 million gallons. The only thing we take out is the algae byproduct. And you can kind of see over time that we'll have a clean zone because we're pumping in the clean water. That clean water obviously is going through a nanobubble system, highly oxygenated. It could be put on the bottom, could be put into the lean system. There's a lot of opportunities of what it could be done with that effluent water. So how would that look? Go ahead, one more slide down. So we looked at it and said, well, if we put a 1 MGD system, that's the picture you saw earlier. That's the clean water coming out, mixing in. If we put a 5 MGD system in, you can kind of get a sense of the size of where that is going. So there's a capability and other tools available that could work and essentially provide some value here to Lake Elsinore. But the real takeaway from what our system does is the physical extraction and removal of the nitrogen and the phosphorus and the carbon. Because by taking the carbon out, you're essentially going to prevent that buildup that we see in every one of our water bodies. As algae grows, they die, they sink to the bottom, then you get a muck layer. You look at that at year one, but now you can look at it over 100 years. You're starting to have a significant muck layer. So we need to find ways to implement innovation that can start turning those faucets off. We've been involved in projects where we've worked on dredging. We've dredged these water bodies, but if they don't turn the source off, that water body returns back to a toxic algae bloom again. So we got to find ways to really link things together that can provide sustainability. So that was our algae harvester hydronucleation system. Quick overview. I know it's the last speak of the day, so I wanted to be brief on that, but I at least wanted to show what we're going to be doing here at Lake Elsinore, hopefully in the near future. So you'll be able to have an expectation of what to see. You'll be able to look at this, understand it. We can sample effluent. We have automation systems on play now. Our harvesters are run by our phones, so we can do the same thing. We can put them on webs and so on. So I'll stop there and open it up to any questions. All right, thanks.